right? Okay. I always forget. Okay. What'd you say? 62?
Yes, sir.
Okay. Okay. Using the tape, this is a bond enthalpy problem, guys. Now, they've done something here with this problem that you have to actually use what you know about Lewis structures to figure this out. Now, the two reactants are easy. The product over here, you need to realize that you've got CH2, which looks like that. You got a double bond here, and you've got C with an H here. Oh, my bad. And it got an I here. Okay. So let's take a look at what we're doing here. So going from the reactant side to the product side, do I still have a carbon-hydrogen bond? Yes, I do. Matter of fact, I have two carbon-hydrogen bonds. So that means that over here, this didn't change, this didn't change, but I did add a carbon-hydrogen bond here. So it looks like I broke a triple bond. That's why I use the strike here. So I broke a triple bond and I broke the HI bond. I formed a carbon-hydrogen bond. I also formed a carbon-carbon double bond because there's no carbon-carbon double bond over here. I also formed a carbon iodide bond. Okay, so it looks like I broke a carbon-carbon triple bond. I broke a hydrogen iodide bond, and then I made a carbon-carbon double bond. I made one more carbon-hydrogen bond, and I made a carbon iodide bond. So the rest is about bonds broken, plus bonds formed. Now, you have to remember that bonds broken will always be positive. Okay, so we're breaking carbon-carbon triple bond. Okay, so we got one of those. We're breaking a hydrogen iodide bond. So we got one of those. Those will both be positive. We're making a carbon iodide bond and a carbon hydrogen bond and a carbon-carbon double bond. So I'm going to, excuse me, apologize for that. So my delta H for this reaction is going to be, this is under standard conditions, bonds broken. I'm breaking a carbon-carbon triple bond. That'll be a positive 839 plus I'm breaking a hydrogen iodide bond. That'll be a positive 299. And then I'm going to add to that all the bonds that I'm forming. And what am I forming? Carbon-carbon double bond. That releases energy. That's why it's a negative 614. I'm making a carbon iodide bond. That'll be a minus 240. Plus another, I'm making a carbon hydrogen bond. That'll be a minus 413. Can you see anything else I broke or made? I think we're good. Nope. So here we go. So we add our all up. So I'm going to say 839 plus 299. And then I'm going to add to that, and I'm going to use parentheses because I don't trust myself with the negatives. And then I'm going to put in a negative 614 plus a negative 240 plus a negative 413. Close my parentheses, and I get, looks like a minus 129. That would be A. So the delta H for this reaction under standard conditions is equal to a minus 129 kilojoules. Make sense?
Yes, sir. Thank you.
It's just bonds broken plus bonds formed. Here's where people go wrong. They'll forget about the fact that you formed a carbon-carbon double bond here. You broke a carbon-carbon triple. You also formed a carbon-carbon double. So make sure that you pick that up, okay, if that's the case.
Yeah, it was just the products that were confusing me.
Yeah, so remember the negative delta H for bonds formed, because when a bond forms, you stabilize all the atoms that are forming the bonds. That's why the bonds formed. They go to a lower energy level. That means you generally release energy as heat. It's an exothermic process, which is why it's a negative delta H.
Thank you.
You bet. Okay.
Can you do
Next,
16?
I hope so.
16.
I really hope so. Let me see. Okay, I gotta change to a mouse here so I can scroll. Okay, it's a naming thing. Okay, which formula is correct? So here's what we're gonna do. We're gonna make the formula or is incorrect. We're looking for the wrong one. So iron 2 sulfite. Here's the way to do this, guys. Iron 2 means you've got a 2 plus iron. Sulfite is SO3. It's got a 2 minus charge. You can do the crisscross, and if you did the crisscross, that would give you Fe2 SO3 2. But there's something wrong with this formula because this is an ionic compound. How do you always write ionic compounds? You always write them as empirical formulas. So you have to get this to the simplest formula, which is going to be FeSO3. Okay? Just make sure all ionic compounds are written as empirical formulas. Okay, let's take a look. Well, this one's going to be pretty easy. I don't even need to look at that formula. Let's just do iron 3 sulfide. So it's going to be iron 3 means it's got a +3 charge. That's what that 3 in Roman numerals means. It means that's the charge on iron. Now, sulfide, sulfur is a halogen. How many electrons does a halogen always want to get to noble gas electron configuration? It wants 2. So that's going to give us this formula. It's going to give us Fe2S3. That is iron 3 sulfide. Why sulfide? Because it's binary. And you know that binary compounds get that pesky IDE ending. Let's do the rest of them just because we can.
You sharing your screen right now?
What's that?
Are you sharing your screen right now?
Yeah, I am. Can everybody else see my screen?
Yes. Yeah.
Yeah.
Okay,
Yes.
so if you can't see my screen, it's on your end. Okay, So let's do the rest of them. Iron 2 sulfate. So that means iron with a 2+ charge, sulfate, also has a 2- charge. It's an SO4 with a 2-. We'll do the same thing we did up here with iron 2 sulfite. We do cross, and that will give us Fe2 SO4 2. But again, you have to write ionic compounds as empirical formulas. So that just gives us FeSO4. Okay, I'm hearing somebody's music or something not okay. Thank you, Jolie. Okay, so let's do iron 2 sulfide. Well, iron 2, Fe plus 2 sulfide minus 2 cross. That gives me Fe2S2. What's wrong with it? It's not empirical. So we have to reduce it. So that gives us FeS. That is iron 2 sulfide. One more, iron 3 sulfite. So that's iron with a 3+ charge. Sulfite is SO3. It's got a 2- charge. Cross, and that will give us Fe2 parentheses SO3, and we'll have 3 of those. And that is exactly what they gave us up here. And that is empirical. So B was our answer here. So learn how to do a little bit of naming, guys. There is naming on this test. And it's naming ionic compounds, and I think there's a molecular compound as well. By the way, know your strong acids. Okay, which one of
Can
the?
you do 34?
Sure. I will do 34 in just a second. This is perchloric. This is hypochlorous. It's a weak acid. This is hydrochloric, which is the easy answer to this question. And this is chlorous acid. And this is chloric acid. Okay, just got to add acid to all of those. All right. What'd you say, 34?
32.
No, 34.
34. Yeah. Okay. Under appropriate conditions, nitrogen and hydrogen undergo the combination reaction to yield ammonia. This is the Haber-Bosch reaction. If the reaction yield is 87.5%, how many moles of nitrogen are needed to produce 3 moles of ammonia? Wow, good problem. Okay, so let's do this. Let's go ahead and figure out, hang on. Reaction is 87.5% nitrogen. Okay, so here's what we need to do. We need to figure out the theoretical amount of nitrogen that is required to produce 3 moles of ammonia, or the actual yield. And then we need to use the 87.5% to figure out how many moles of nitrogen are needed to actually produce the 3 moles of ammonia. That's a mess. So we're going to figure out how many moles of nitrogen required to produce 3 moles of ammonia. Keeping in mind, this is 87.5% yield. So we've got 3.00 moles of NH3. And we just do the math. Okay, and we use the mole to mole ratio. So the mole to mole ratio is, this is moles of NH3. So we have 2 moles of NH3. And then that's going to produce 1 mole of nitrogen. Okay, so if this is the actual yield, okay, this is the actual yield because that's what they want to produce for ammonia. So that's going to be 3 times 1 divided by 2, which gives me 1.50 moles of N2. But this is the actual moles of N2 that produce the 3 moles of ammonia. But what we need to do is we actually need the amount that we need to get an 87.5% yield. So let's take a look at that. So I've got 87.5 divided by 100 is equal to 1.50 moles. So what I need to do here is divide this by 87.5. So 1.5, hang on, 1.5 divided by, and actually 0.875 divided by 0.875. What do I get?
Your screen is froze.
Mine is frozen? I don't think so. I think I'm okay. Might be you. So 1.71 moles of N2. We can check that out. How many moles of NH3? Is my screen frozen for everybody or just one person?
No, you're good.
No, it's
Yeah,
fine.
you're fine.
Okay, I got 1.71 moles of N2. My ratio is 1 mole to 2 moles of NH3. All right, let's see. So that's 1.71 times 2, which gives me 3.42. But my percent is 87.5%. So I'm just going to, so if it's 87.5% yield, I'm just going to multiply that by 0.875. Which gives me 3 moles. Okay, so it looks like 1.71 moles is the answer.
Can you show the process of you getting 1.71, like not the whole process, but after the 87?
So I started with the 3 moles produced. I did the mole to mole ratio, which gave me 1.50 moles of nitrogen that I needed actually. But it's only an 87.5% yield. So how do we do percent yield? We take actual divided by theoretical times 100. Okay. So what are we looking for? We're looking for the theoretical amount that I need to start with. And so this is what we're after. But this is equal to 87.5%. Okay, so this is what I'm solving for. So really, what I'm doing here is I'm multiplying both sides by the theoretical. That's times the theoretical over here. This is going to cancel over here. So that gives me actual times 100, which is equal to, okay, let me clean up some space here. So I've got actual times 100 is equal to theoretical times 87.5. Okay, so this is what I'm solving for. And so 87.5, so if I divide the actual by the 87.5%, which is over, it's 87.5 per 100, okay? That all cancels. So what I'm actually doing is dividing the actual by 87.5 divided by 100. The actual was 3 moles. So I'm dividing by 0.875. That's where I'm getting the theoretical, which is 3.42. And then I just back calculated, okay? How did I back calculate? Let me erase all that so I get a little bit of room. That was pretty messy explanation, sorry. So I came up with 3.42, and I want to know how many moles of N2, if I start out with 3.42 moles of NH3, which is the theoretical yield, and then my ratio is 2 moles of NH3 to 1 mole of N2. And that's where I came out with 1.71 moles of N2. So let's see if we can come up with an easy way to do this. Remember that 87.5% is actual over theoretical times 100. Okay. What we're looking for is this, and it's based on the fact that the reaction is 87.5% efficient. So we have to solve for the theoretical yield. Once you get the theoretical yield of the ammonia, you can use the theoretical yield of ammonia to figure out how many moles of nitrogen you need to begin with. That was pretty messy, guys, and probably not very good, but we did actually come up with an answer. I say let's move on.
Can you do number 37?
I can try. Hope I do a better job on 37.
We asked for you to do 32 like multiple times. Do you
All
think you
right,
can do it?
all right. Well, how did you ask me?
like 4 times.
4 times.
How?
But it's okay because other people were talking over us.
All right, well, shame on them. So we'll do 32 and then we'll do 37. How's that? Under,
That's perfect. Thank you.
okay, under appropriate conditions. Okay, we got same damn reaction. A blank gram as sample of N2 requires 3 grams of H2 for a, so this is just straight up stoichiometry. X grams of N2. We got, this is a gram to gram stoichiometry, okay? And we've got 3.0 grams of H2. What do you have to do when you're given grams and you're asked to do stoichiometry?
Convert to moles.
Convert to moles. So this is going to be grams to moles. Then what's next? Mole to mole ratio. This will be moles of H2 to moles of N2, which is what we're looking for. And then finally, moles of N2 to grams of N2. Here we go. So H2 has a molar mass of 2.02 grams. The mole to mole ratio is 3 moles of H2 to 1 mole of N2. 1 mole of N2 weighs 28.02 grams. Okay, I know that's pretty messy. So that's 3 divided by 2.02 times 1 divided by 3 times 2802, 28.02. And I come out with 13.9. Hopefully that's there. 13.9 grams. What's my closest answer? Looks like 14. Somebody check the key. Make sure that's correct.
Yeah, that's
It
correct.
is.
Okay, 13.9 rounded up to 14. Now we're doing 37. Are the 32 cranky people happy? Or do I need to make my handwriting better? Wow, no response at all.
I feel embarrassed.
Me too. Especially after that last problem.
No, it's because I knew it, but I just kept putting the 3 moles on top of the grams of H2 for some reason. So that was
Okay,
my
look, just make sure the units cancel. So this is grams of H2 canceling. This is moles of H2 canceling. I should have put an H2 up here so you could see that it's moles of H2 canceling. This is moles of N2 canceling. So in stoichiometry, it's like dimensional analysis. It is dimensional analysis. You just need to make sure that you're dividing by the same unit and then you're multiplying by a different unit. So this is grams times moles times grams. And this is dividing grams by grams, moles by moles, moles by moles of the same thing. Okay, so just keep that straight and you'll be smiling. Okay, smiling might be a stretch, but you know, we'll give it a shot. All
Can
right,
you go over 40 after 37?
yeah, we're doing 37 first or I'm going to get chewed out. Okay, this is a good one. We're going to do oxidation numbers. Okay, so we got NH4. So the way to do this, guys, is this. Okay, so you
Can you scroll up?
Can I scroll up? Like this? Scroll down or scroll up?
Thank you. That's enough. Thank you.
Okay, got it. You know, you can make your screen bigger or smaller at home if you're playing at home. All right, so this is NH4Cl. And the way we do oxidation numbers, you generally start with the most electronegative. That's actually nitrogen in this case. So that's going to be a -3. Chlorine is the next at -1. This is a compound, so it has to equal 0. And so I've got a -1 and a -3. So this has to be a +4, but I got 4 of them. So that's a +1. What are we looking for? With the compound that has the atom with the highest oxidation number. So far, the highest oxidation number is +1. I'm betting we can beat that. All right, here is calcium sulfide. And this one's easy. Sulfur is a halogen, not a halogen, a chalcogen. They all want 2 electrons, so that's going to be a -2. Calcium is an alkaline earth metal. They're always +2 in compounds. So right now, calcium's the winner. Then we have magnesium sulfite. So we have magnesium and SO3. Split them up. Oxygen is the most electronegative at 2, -2. 3 times a -2, -6. Remembering that everything has to have to 0. Magnesium is +2. And so here is poor old sulfur. We've got a +2 and a -6. That means this guy is a +4. So far, sulfur in magnesium sulfide is the winner. Let's see if we got anything better. I think we do. We've got aluminum nitrate. We got 3 of these. We split them up. Okay, aluminum is always +3 in compounds. Oxygen gets its charge, which is -2. I've got 3 times 3. That's 9 of them. 9 times a -2 is.
3 times 2.
I can't hear you. What? Oh, that's nitrite. You got it. You got it. You got it. Okay, I couldn't understand that, but you're absolutely right. That's not aluminum nitrate. It's aluminum nitrite. Thank you. Split them up. Aluminum still +3. It doesn't care. Okay. Oxygen is still -2. It doesn't care either. 3 times 2 is 6. 6 times a -2 is -12. So my total charge over here on nitrogen is what? 3 times 2 is 6. 6 times a -2 is -12. What's my charge got to be over here? Plus
9
what? Plus what?
plus 9.
Plus 9. I have 3 aluminums, so I have to split that plus 9 up between, I'm sorry, 3 nitrogens. I have to split the plus 9 up between the 3 nitrogens, so that makes it +3. So right now, sulfur is still the winner over here. Then I have Na, N, and so this is -3. This is always going to be +1. So looks like my answer is sulfur and magnesium sulfate at a +4. That is answer C. Hopefully that's the right answer.
Wait, can you explain why it's not D again?
Why it's not D? Because sulfur is +4, nitrogen is +3.
Okay, cool.
Okay, and +4 is the highest oxidation state. And that's sulfur. That was kind of a nasty problem. You had to do every single one, and you have to not make the mistake I did of assuming that was aluminum nitrate, which is a more common aluminum nitrogen compound. Okay, so that's how you do oxidation states, guys. Remember that if you're doing something like this, this has a charge. And so everything has to add up to the charge on the polyatomic ion. So oxygen is the most electronegative. It will get its charge. 4 times a -2 is -8. And so that's going to be a +5 to give you the charge that's on the ion. So just remember that. The only thing that has to add up to 0 are compounds, because all compounds are electrically neutral. Okay, what else?
40.
Can we do 38?
Okay, somebody was ahead of you that time. They spoke up first. So did you say 30?
No, I said 40.
40. Okay, let's do 40 and then we'll do 38. Okay, which of the following would require the largest volume of 0.1 molar sodium hydroxide? So here's sodium hydroxide, guys. This is going to be an acid-base reaction. And what they're talking about is going to neutralization. And that's where you get salt and water. Okay, that's going to depend on volume times the molarity. And every one of these acids is a little different. So you have to know the formulas for your acids to know. Here's the bottom line. The bottom line is H pluses plus OH minuses. The more H pluses that you have, the bigger the requirement for hydroxides. So that's all about volume times molarity. And here's what you need to remember. Volume times molarity. And molarity is, in this case, since these are all acids, moles of H plus over the volume of the acid. The volume will cancel, and that's going to give you moles of H plus. Volume times molarity equals moles. You need to say that like 10 times before you go to bed. Volume times molarity equals moles. All right, so let's come up with formulas for our acids here. Perchloric acid is H3. Sorry, it is not H3. Let me actually erase all of that. So perchloric acid is a monoprotic acid, HClO4. So I have 10 mils, everything's in milliliters. So you don't need to worry about converting to liters. So that's going to be 10 mils times 0.05 moles over volume. Don't worry about the milliliters. Don't worry about liters. Just whatever is going to give you the biggest number, 10 times 0.05. Here you've got hydrobromic, another monoprotic acid. You've got 15 mils times 0.05. Well, we don't even need to do the first one because right now I have a larger volume and the same concentration. So this one wins over this one, but that's probably not going to be the answer. But let's take a look. So we've eliminated A. Now we've got B as our answer, but this time I've got phosphoric acid, which is a triprotic acid, and I've got 10 mils of it. So I have 10 mils times 0.05, but now I have to multiply times 3 because I've got 3 protons for every 1 mole of phosphoric acid. For nitric acid, its formula is HNO3. I've got 20 mils of it times 0.05. And that's, again, since nitric acid is monoprotic, there's only one, you could say times 1. Remember, this one's times 3. And then I have sulfuric. That might present a problem because sulfuric is H2SO4. And I've got 5 mils of that times 0.01. Well, even though this is a diprotic acid, I have 1/5 of the concentration, and I have a quarter of the concentration of the or volume of the 20 mils and half the volume of the 10 mils of the triprotic. My guess is the answer is going to be C without doing any of the math. Okay, so let's go ahead and do C, see what we get. I've got 10 times 0.05 times 3, which gives me 1.5 moles of H plus. I'm not even worried about this, but let's go ahead and do it anyway. So that's 5 times 0.01 times 2, which just gives me 0.1 moles of H plus. This one here, I've got 20 times 0.05 times 1, which is 1 mole of H plus. And then up here, 15 mils, 15 times 0.05 times 1 gives me 0.75 moles of H plus. And then 10 mils times 0.05 times 1, which is 0.5 moles of H plus. So whichever acid gives you the most moles of H plus will require the largest volume of sodium hydroxide. Just remember that volume times molarity, which is moles over volume, it's actually in liters, but that's okay. That gives you moles because the volumes will cancel. And if you have H plus plus O plus OH minus makes H2O, however many moles you've got of this will require the same number of moles of hydroxide. Make sense?
Yes, sir.
Okay.
I have a question.
Okay.
I don't know, it might be dumb, but why is A not times 4?
Because the only thing I have 4 of is oxygen, not hydrogen.
Okay.
I don't care about the oxygen. It's the H plus that is reacting with the hydroxide. This is the net ionic equation for really any acid-base reaction, not really for a weak acid base reaction, but still it's really the H plus on the acid and the hydroxide on the base that make the water. This is the reaction right here.
Okay, thank you.
Yeah. Okay, somebody asked for what?
38.
38. Thank you. 0.1 molar solution of blank will contain the highest concentration of potassium ions. This is a naming problem, guys. This is about knowing the name of or the formula for all of these. So bottom line, here's potassium. It's got a +1 charge. Phosphate is PO4 with a 3 minus charge. So cross, that gives you K3PO4. You have the same concentration of each one of these guys. So none of these guys are going to give you as much potassium as potassium phosphate, but let's go ahead and finish naming them. So we have potassium with a +1. Hydrogen carbonate is this. You guys might not be that familiar with hydrogen carbonate, but you are with carbonate. Just stick on a hydrogen. Now, carbonate, which you learned, has a 2 minus charge. If I stick on a hydrogen with a +1 charge, the intact hydrogen carbonate ion becomes a -1. So this is -1 and a +1. So that just becomes KHCO3. So that's just a 1-for-1. Potassium oxide is K2O because oxygen has a -2, potassium has a +1. That's why the formula cross, that's why you have K2O. So that's 2 potassiums. Still, the 3 potassium wins. And this is just about naming. Potassium iodide. Potassium is +1, iodide -1. Cross. That just gives you Ki. So you only get 1 potassium. And then potassium hypochlorite. So potassium, here's hypochlorite, ClO with a -1. It's a crisscross. You get KClO. Okay, so A is the obvious winner. Look at that phosphate. There it is. Big old thing with a 3 minus charge. Look at that potassium. It's an alkali metal. They all have a +1. When you crisscross, you get the empirical formula of K3PO4. 3 potassiums for every 1 potassium phosphate. Okay?
Thank you.
You bet.
Could we do question number 33?
I hope so. Hang on. You guys can still see my screen, right?
Yes.
Yeah.
Okay.
Quick question about the final.
What's that?
Is the final gonna count as a 5th grade, or does it only replace the lowest grade?
Oh, no. It's 15% of your exam average. You got to take the final. It's mandatory. Or if you choose not to take the final, you lose 15% of your course average.
Okay.
And if you score higher on the final than one of your regular exam grades, it will replace that regular exam grade. So potentially the final could be worth 30% of your course average. That's why it's so powerful.
When it gets applied to the lowest grade, is that with the curve points as well?
Oh, yeah. I mean, if your curved final score is an 80 and you've got a 30 dragging you down on one of your regular exams, you lose the 30 and it gets replaced with an 80.
Okay.
How much will the curve be? And
I am not telling. I will tell you that it's substantial. And
Will you count if we're at like a 88 something at the end, maybe?
I'm not, I don't do it that way. What I do, wha- stop, Mylene, you're laughing at me. That's just embarrassing. So that's okay. I don't mind.
I'm-
I've been laughed at
My
before.
friend.
What?
I'm laughing at my friend.
Oh, okay. So the deal is what I do at the end of the semester, once all the grades are in, and I'm very careful about that. You're not going to see all of the grades probably in until, well, you may see all the grades in, but I won't have made my decision about letter grades probably until Tuesday next week. Okay. What I do is I do a descending sort of both sections of my Chem 1 and from high to low, and I figure out where the grade breaks are. And the grade break could be, if grades are high, could be 90 to 100 is an A, could be 89, might be 88. I cannot tell until I do that process. It's a little different every semester. So I can't tell you that an 89 is an A. I can't tell you, I can tell you 90 is definitely an A because that's traditional. I can't tell you 88 could be an A, but I won't know until.
Does that mean does that mean 79 will stay a B? I mean, a C.
79.9 or something.
70, yeah.
It's the same thing. 80, if the natural break is 80 and above, that'll be a B. If it's a 79, that'll be a B. If it's 78, that'll be a B. It depends on the grades in the class. Every class is different.
Okay, thank you.
Yeah, now the only arbitrary grade I do is for a D. I arbitrarily establish a D at 55. So I don't see any reason not to let people escape if they're not chemistry majors, if they're not science majors. And, if your major is psychology or sociology and it doesn't require a C in chemistry, I see no reason to hold you back. Okay?
Thank you.
Yeah. Okay. All right. What was the question? What question did you ask?
33.
33. Okay. Let's see what we got. Okay, this is a limiting reactant problem. I've got up here, I've got 2.5 moles of O2, and I've got 4.6 moles of propane. While we're on the subject, this is a hydrocarbon, a compound composed only of carbon and hydrogen. It's a combustion reaction. It's also a redox reaction, and a combustion reaction of a hydrocarbon produces two products, carbon dioxide and water. And in this case, I'm looking for moles of water. I want to know how much I can make theoretically. So the first thing I need to do is figure out what is my limiting reactant. So I'm going to figure out how many moles of propane, C3H8, I have to work with. I've got 4.6 moles. And then for oxygen, this is X moles of O2. I've got 2.5 moles. All right. Now, all I have to do here is divide by the coefficients. Well, this one's pretty easy. The coefficient of propane is 1. The coefficient of oxygen is 5. And I start out with fewer moles to begin with. So this is going to be obvious that oxygen is my limiting reactant. We'll go ahead and divide. So that's going to be 2.5 divided by 5, which gives me 0.5 moles of O2. Since I was only divided by 1 here, that's just going to be 4.6. So this is not my limiting reactant. We're going to do something else with this, but this is going to control how much water I can produce. So I'm going to do it down here where I have a little bit of room. How many moles of H2O can I produce if I've got 2.5 moles of O2? The only conversion I have is the mole to mole ratio. I can make 4 moles of H2O from 5 moles of O2. So 2.5 times 4 divided by 5. So 2.5 times 4 divided by 5 says I can make 2 moles of water. That should be my answer. So the answer should be D if the universe is still working.
And if you were given grams of like O2 and C3H8, would you just convert grams to moles and then divide by the coefficient?
Correct. That's exactly what you would do. I mean, we could even do
Okay,
that by multiplying 2.5 times 32 and 4.6 times the molar mass of C3H8, but we're not going to do that. Here's what I do. Here's what I do want to do. What I want to do is figure out how many moles of C3H8. Matter of fact, let's figure out how many grams are left over. Okay. Since we know that 2.5 moles of O2 are what we start with, we can figure out how many moles of C3H8 that we use. And that we just start with our limiting reactant, 2.5 moles of O2. Then we do the mole to mole ratio, 5 moles of O2 will use 1 mole of propane, C3H8. Not going to use very much. 2.5 times 1 divided by 5 says I'm really only because moles of O2 cancel, I'm really only using 0.500 moles of C3H8. So how much did I start with? 4.6 moles minus 0.5 moles that I used, which leaves me with 4.1 moles of C3H8 remaining. Okay, does that make sense?
Yeah.
Yes.
Do you think there'll be a question like that on the final?
I don't know. I'm just making sure that you know how to handle it. If there is.
Can you go over number 44?
I hope so.
I have a question. You said you don't know what the questions are, right? For the final.
I really don't.
Uh-huh.
I mean, I don't have a final sitting here in front of me, and I haven't really looked at it in a year or so. But when I originally designed my course, and we revise courses all the time. A couple of years ago, I looked at the questions on the final, and I tried to make sure that I covered at least 95% of what you might see on the final. That's no guarantee that you're gonna, be able to handle the questions because it's been a long semester. You might have forgotten. I mean, what did we do at the beginning of the semester? We did, dimensional analysis, naming, isotopes, molecular formulas, ionic formulas. I mean, all of that stuff was a few months ago. Human beings, that stuff might still be in there, but it might be really hard to pull out of your brain. Let me go ahead and do 44 here. All right. So for which one of the following reactions is equal to the heat of formation of a product? All right. So this might be a little obscure, but heat of formation of any product, this is tabulated data. Okay. This is how you wind up doing the delta H equals delta H of formation of products minus the delta H of formation of reactants. You have the delta H of formation of individual products. The requirements are elements as reactants in standard state, okay, combining to form 1 mole of a product. Okay, so that's how we're going to evaluate this. We're looking for reactants that are elements in their standard state or elemental form. That means if you have something like carbon, it's graphite, not a gas. It's a solid. If you have something like chlorine, it's a gas. This is testing whether you know what form elements are in. Now, almost every element on the periodic table is a solid, but there are exceptions. You have your gases like H2 gas, your diatomic molecules, N2 gas, and O2 gas, F2 gas, Cl2 gas. Br2 is actually a liquid. It's one of only 2 liquids at room temperature and atmospheric pressure, standard conditions, that's actually a liquid. The other one is mercury, which is a metal. And then iodine, I2, it's a diatomic molecule. It's a solid. Every other element that's on the periodic table is a solid. And just remember that mercury, Hg, is a liquid in its standard state. Okay? But you do have to remember your gases and your diatomic molecules. So let's go through this. Now, is carbon in its standard state, in its elemental form, a gas? No. So that means that cannot be the correct answer. Okay. I don't have to look at anything else, but let's see what else is wrong. H2 gas. This is fine. Check. Oxygen. Does oxygen run around as a monoatomic atom? No. It runs around as O2. So that's incorrect. Now, this is, I don't know what the fuck it is. Oh, I apologize for my language. That was horrible. I apologize. This is some kind of a sugar, but this is okay, except I don't know why it's a gas. All right, here we go. Carbon, solid. That's okay. Does hydrogen run around as a monoatomic atom H? No, that's not okay. This is benzene, which can be a liquid, so that's okay. But we've already dismissed it, so that can't be it. How about this? I've got nitrogen gas. That's okay. Oxygen gas. That's okay. And I have 1 mole of nitrogen dioxide. This entire reaction is a heat of formation reaction. So C will be your answer. Let's figure out what's wrong with the rest of them. N2 gas, that's okay. H2 gas, that's okay. 2 NH3s, no, it has to be 1 mole of a product. So that is not okay. Phosphorus. Phosphorus is a solid. Most of the elements on the periodic table are solids. Hydrogen does not run around as a monoatomic gas. It runs around as H2. So that's not okay. Bromine, number 1, not a gas, and it's diatomic in its elemental form. And so that's not okay. This whole reaction is a mess. And this is an ionic compound, and ionic compounds are solids, not liquids. Okay, so C is the answer to 44.
Thank you.
Can you do 67?
67. I hope so. Let me look. Damn it. Oh, I forgot to erase. Hope it still erases. Oh, thank God. All right. Oh, 67, sigma and pi bonds. Guys, this is the easy one, but we're going to redraw it a little bit. Okay, because I know stuff like this bugs you guys. Okay, but it's really simple. So here we're going to just redraw it. We've got CH3. All you got to do, put your carbon like this. This is a tetrahedral carbon, which is singly bonded to CH2. Just hang your H2s out there. And then what do we got? We got another single bond to carbon with 1 hydrogen hanging off of it. Then we got a double bond. Remember, you can only make 4 bonds to carbon. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. So that means we can only put 2 more bonds on this carbon. So it's bound to be a CH. So we'll just throw that up here. And then here's our 4th bond. It's going to another carbon. And that's going to be a methyl group. Sorry, a methane group. And then let's see, what do we got? Got that. Okay, we're going to have 1 bond. And then we got a triple bond to C and then an H. Now, as far as sigma bonds, that's the symbol for sigma. This is the symbol for pi. You're probably more familiar with that. We're just going to count them. Every single bond has a sigma bond. Every one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 67 has 16 sigma. So I don't see any other answer with 16 sigma. I haven't even counted pi bonds yet, but I know there's going to be 3. Every double bond has 1 sigma and 1 pi bond. Every triple has 1 sigma and 2 pi bonds. We already counted the sigmas. We got 2 pi's here, 1 pi here, for 3 pi's. Okay, now I know that this might give you trouble. You're not going to be able to write on the exam, but you can redraw it. Just remember, carbon only makes 4 bonds. So if you have an H3C, there is the H3C. A little bit of organic chemistry for you. Then you're going to have 1 more single bond to the carbon because you can't have more than 4. And then there's your CH2s right there. That's 1, 2, 3 there. So you can only have a single bond here. Then you have 1 carbon hydrogen bond. Then you got a double. That's 1, 2, 3, 4 bonds to carbon. That's all it can make. And then 1, here's your other CH, 1, 2, 3, 4. That carbon has 4. And we're going to do something else with this real quick. Got 1, 2, 3, 4. And then when you've got a triple bond between the carbons, you can only have 1 single bond on either side of it. Okay. Now that we've done that, let's look at in a different way. We counted the sigmas, we counted the pi's. I want to know, what is the electron geometry around this carbon? It's got 1, 2, 3, 4 things around it. What's the electron geometry?
Tetrahedral.
There you go, tetrahedral. Any non-bonding electrons?
No.
No. So what's the molecular geometry?
Tetrahedral.
Tetrahedral. What's the hybridization around this carbon? I need 4 bonds or 4 equivalent orbitals. They all start with S. I need 3 more.
sp3.
sp3. Tetrahedral. The electron geometry determines the hybridization. So I've got 1 plus 3 equals 4 equivalent orbitals. sp3 hybridized. Let's go down to this carbon. I've got 1, 2, 3 electron domains. What's my electron geometry?
Trigonal planar.
Trigonal planar. What is my molecular geometry?
It's the same.
Same. Trig. Planar. What's my hybridization?
SP2.
sp2. Good job. Okay, let's go down to this carbon. Okay, this one right here. What's my electron geometry?
Linear.
Linear. What's my molecular geometry?
The same.
Linear.
Linear. What's my hybridization?
sp.
That's it. Good job. All right, one more thing. What's my bond angle around that carbon?
109.5.
109.5 degrees. Good job. What is my bond angle around that carbon?
120.
120. What's my bond angle around this carbon?
180.
180. All right, not bad, guys. Okay.
What constitutes a trigonal pyramidal?
Okay, let's take something like PH3. You have to draw the Lewis structure. There it is. I've got 1, 2, 3, 4 things. So my electron geometry is tetrahedral, but my molecular geometry is different because I got this non-bonding pair of electrons pushing down in all 3 on all 3 of these bonds. So that creates something that looks like this. a little three-sided pyramid. Remember, you got those non-bonding electrons that are poking up there, causing this trigonal pyramidal shape. That's trigonal.
So trigonal pyramidal can only be in the molecular geometry.
That is right. So
Thank you.
let me ask you something else. Is this molecule pH3 polar or nonpolar? Look at the shape. Is the shape asymmetrical?
Yes.
No, it's
So it's
polar. It's polar. So something like NF3, that's a polar molecule. NH3, that's a polar molecule. You've got this trigonal pyramidal shape. While we're on the subject, if you've got a bent geometry, polar, technically it needs polar bonds, but I rarely see these asymmetrical geometries without polar bonds. Let's say you've got trigonal, pyramidal, okay, polar. Technically, polar bonds and an asymmetrical geometry. You've got seesaw. This is seesaw. It's got a trigonal bipyramidal electron geometry, seesaw molecular geometry. Let's say the bonds are polar, the molecule is polar. Asymmetry is what's telling you that. T-shape, which has two non-bonding pairs on a trigonal bipyramidal electron geometry. This is T-shape. Polar. When I say asymmetrical, I'm just saying one side doesn't look like the other side. This side is radically different from this side. That creates a dipole moment because the bonds can't cancel in these kinds of shapes. There's one more, molecular geometry. This is based on an octahedral. There's a non-bonding pair of electrons down here. This is called square pyramidal. That with polar bonds is polar. So any asymmetrical geometry, let's take a look at one of the most polar molecules around, guys. And we love this molecule. We love to drink it. We love to play in it. We love to bathe in it. We love to fill our hot tubs and our swimming pools in it. We like to go to the ocean and swim in it. This guy is polar, and it's a tiny molecule, but it has really strong hydrogen bonding because hydrogen bonds actually in 4 different directions. It's pretty darn unique. It's one of the only substances that has a lower density as a solid than it does as a liquid. Good old water. 70% of the mass of your body is water. You got a lot of it in you.
Wait, I had a question.
Yeah.
So on octahedral, say if there was 4 non-bonding pairs, it would be linear, right? So would that make it non-polar? Since
You're not going to octahedral won't do it. Okay. So let's do that. So xenon tetrafluoride. You're not going to have 4 non-bonding pairs because that would put non-bonding pairs at 90 degrees, and it's so energetically unfavorable that it doesn't happen. Okay, so you've got 8 valence electrons here. And you can have 2 non-bonding pairs, okay? But you're not going to get 4 non-bonding pairs. We've got 4 times 7. 4 times 7, 28 plus 8. What is that, 36? All right, so here's xenon. Let's throw the fluorines out here. Okay, now there are 8 non-bonding, there are 8 electrons. We fill the octet around the fluorine. 8 times 4 is 32. So I only use 32. I've got 36. So I need 4 electrons to go somewhere. That's 2 non-bonding pairs. Okay, so you're going to have a pair here and a pair here. They'll be completely on opposite sides of xenon. This is a non-polar molecule. And the geometry is a square, but they're all in the same plane. So we call this square planar. Okay, and it is non-polar. I think I know what you're talking about, and that would be something like xenon difluoride. So we got 8 plus 2 times 7. 2 times 7 is 14 plus 8. Somebody come up with that for me. Is that 22? All right, so xenon, got fluorine out here, fluorine out here. And let's go ahead and complete the octet. I'm going to give xenon its octet: 2, 4, 6, 8, 10, 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 2 more electrons. I only used 20. 2 have to go somewhere. They go on the central atom. So our electron geometry is 1, 2, 3, 4, 5. So our electron geometry is trigonal, bipyramidal. Our molecular geometry is linear. All of the non-bonding pairs go in the equatorial region. So I'm going to redraw it a little bit differently. This is xenon with a fluorine here and a fluorine here. Both fluorines are in the axial region, and the non-bonding pairs of electrons are in what is called the equatorial region. Okay, so this is the bond angles here are now, you're right, it's linear, so it is 180 degrees. But normally, and let's do something like PCl5, which is an easy one to draw. We've got phosphorus, we've got a chlorine here, a chlorine here, a chlorine here, here, and here. Now I've got 120-degree bond angles between all of the equatorial chlorines, and I have 90-degree bond angles between the axial and the equatorial. Okay, so these are the axials. These are the equatorials.
Are you gonna know the difference between axial and equatorial regions?
You should, because the equatorial regions are where non-bonding electrons have to go in trigonal bipyramidal. The reason is you can't have a non-bonding pair of electrons at 90 degrees. You can't have, let me see if I can even do this. So if this were xenon, this is a non-bonding pair of electrons. you can't have non-bonding electrons at 90 degrees to each other. It's so energetically unfavorable that it doesn't happen. You have to have the non-bonding electrons at a minimum of 120 degrees from each other in the trigonal bipyramidal electron geometry. Okay. All right, we accomplished a lot with that. What else you got? You guys are staying up awful late. I don't know how smart that is, but I'll stick with you for a little bit longer, and then I have to go in early tomorrow to do some stuff. So I'm going to try and get to bed at least by midnight.
Can we do question 47 or 48?
I hope so. Didn't we already do that?
Oh, did we?
I don't know. I don't know. I'm kind of getting wiped out here, so I could.
We haven't done that one yet.
Okay, great. Oh, 47 is nice. Okay, yeah, that's both are good. Okay, let's do 47 first. And it's different than what we've been doing. These are all delta H of formation. So this is the delta H of formation, products minus reactants stuff. Okay, so delta H of the reaction under standard conditions equals, this is going to be the delta H of products, the sum of the delta H. So here are our products. Okay. Wow. That is an ugly compound. But okay. Calcium, that's kind of an arsenic acid. But at any rate, I only got one of them. So look at them. It's minus 2346. Minus 2346.0 plus 2 waters. 2 times, here's water, minus 285.9. Okay, minus, here we go. My 2 reactants, I got calcium hydroxide, just got one of them. So it's a minus 986.6. Plus, we got 2 of these things. That's arsenic acid, minus 900.4, and there's 2 of them. So don't forget to multiply by 2, minus 900.4. That's a 0.4. And then boom. All right. So that's just products minus reactants. So it's going to be minus 2346 plus 2 times a minus 285.9 minus 285.9 minus, and I'm going to use parentheses on this because I don't trust myself on changing signs. Okay, so this is going to be a minus 986.6 plus 2 times a minus 900.4. It's really good if you know how to use your calculator, guys. Okay, I think that's got it. I got a minus 130.4. Okay, so my delta H for this reaction under standard condition is minus 130.4 kilojoules. So the answer better be C. Somebody can check that out. All right, let's look at 48. Sample of iron is absorbs 81.0 joules of heat, upon which the temperature of the sample increases from 19.7 to 28.2, the specific heat of iron. All right, so look, one thing I'm pretty sure is you guys are not going to get any formulas. So you simply got to know them. Okay, so this is the specific heat formula. This is the specific heat. This means that under constant pressure is equal to Q. That's the amount of heat that's absorbed divided by mass times delta T. So delta T is always temp final minus temp initial. Okay, so we want to solve for, what are we solving for? Solving for mass. So they're giving us this, they're giving us this, and they're giving us the ability to do a quick calculation of that, and they want us to solve for mass. So all you need to do is algebraically manipulate the equation. We're going to multiply both sides by mass, and we're going to divide both sides by the specific heat. All right, I know that's a mess. Mass will cancel, specific heat cancels. I get mass is equal to Q in joules divided by specific heat times delta T. The rest is finding out what the numbers are. They've given us Q, they've given us specific heat. We just need to figure out what the hell is the delta T. So delta T, I'll just do it up here. What are we doing? It's going from 19.7 to 28.2. So that's going to be 28.2. That's temp final minus 19.7. So 28.2 minus 19.7. It gives me 8.5. 8.5 degrees Celsius. So let's plug and chug. Mass equals Q, 81 joules, divided by specific heat, 0.450 joules per gram Celsius times the delta T, which we just figured out was 8.5 degrees C. Make sure that all the units cancel. If you're going to plug this in your calculator, guys, and you're going to do this denominator here, you need parentheses around the denominator. So that's going to be 81 divided by, I'm going to set up a set of parentheses, 0.45 times 8.5. I'm going to close my parentheses. That's going to give me 21.2. My mass should be 21.2 grams. There it is. Let me just give you an obvious. There's no such thing as negative mass. It does not exist. Now, if we can figure it out someday, maybe we'll have anti-gravity, but right now that doesn't exist. So don't fall for that if you're figuring mass. And obviously they put it there. If you did 19.7 minus 28.2, if you fail to realize that it needed to be temperature final minus temperature initial, you would come out with minus 21.2. Don't fall for that. Little bit more then, and then I'm pretty gassed.
I have a question.
Yeah.
Do you think it helps like reviewing like the past exams, like like really focusing, or like it's kind of this review right now?
I've given you 4 exams
Yeah.
and you have worked solutions for all 4 of those exams. There are questions on this exam, this practice final, and trust me, this practice final is just an assembly from the same test generator that I use to build my exams. So do I think they're both valuable? Yeah. But the advantage you have with the 120 questions on my exams is that I have worked solutions on them all. And you just don't have that much time to study and to get proficient. So if you're having trouble solving one of these equations or one of these problems, look on the, first of all, when did we do thermodynamics? That was chapter 5. What test had chapter 5 on it? Was that test 2 or test 3? I think it might have been exam 3. So you go on exam 3 and see if you can find something similar. And you look on my exam and you say, oh, this is how you work that problem. So it's kind of a combination of them. Between my exams, there's 120 questions, and this is 70 questions. That's a total of 190 questions, and you do have a key. I don't know how many we've worked tonight, but we've worked a few. And if you've been focusing, paying attention, you have a clue as to how to work certain types of problems. On the final exam, you're not going to get 100%. Is that something to shoot for? Absolutely. But I've been doing this for 20 years, and we haven't been using the ACS final that long, but close. I've never had anybody get 100% on the ACS final. I've had some people get very close. I took this final when I was an undergraduate, and I finished in the 85th percentile, which is really very good, but it's not top drawer. I was just an ordinary undergraduate who worked really hard and was able to do this stuff pretty well. But I didn't get 100%. Anyway, that's my take on it. I know that's not satisfying in the time that you have to study for this, but I would work as many of the problems as you possibly can. I would make sure, if I did nothing else, I'd make sure I was 100% on all 4 exams that I've given you. You have experience with those, and you have worked solutions for all the problems.
Yeah, thank you so much. That helps a lot.
Okay.
I
Hey,
have a question.
yeah, go ahead.
Can you do number 69? I mean, yeah, 69.
Sure. All right. Are you sure you don't want to do quantum numbers?
I'm sure.
Okay.
Okay.
Okay, this is easy. This is an easy one. And sounds like something they might put on the final. Of all the following gases, which will have the greatest rate of effusion? So I'm going to give you a little chart here. All right. So these are gases that are in a mixture. So let's just pretend you've got all these gases, HCl, HBr. They're all in a balloon. NH3. Wow, this is a nasty balloon. CH4. Don't light a match because this thing will go absolutely nuts, blow up in your face. Did I get them all? Argon, CH4, NH3, HBr. All right. Now, They're all in the same container. That means they have the same volume. That means they have the same temperature. Now, here is what is true about all the gases in a mixture of gases. They all have the same average kinetic energy. Okay, the equation for kinetic energy is 1/2 times mass times velocity squared. Don't worry about the 1/2. Don't even worry about the square. Just look at mass times velocity. Okay, and having some relationship to kinetic energy. Yes, you would need to, if you really wanted to calculate the kinetic energy, you would need the 1/2 times mass times velocity squared. But here's the deal. If this number is the same for all these gases, HCl is like 36.46 grams per mole. HBr is something like 80 grams per mole. Ammonia is like 17 grams per mole. Argon, I think, is 40 grams per mole. Methane is like 16 grams per mole. So they all weigh different amounts. That's mass, but they all have the same average kinetic energy. So we're just looking at mass times velocity. Well, if I'm a lighter gas, I have less mass. And I have this kinetic energy, what does that say about my velocity? My velocity has to be higher. And all these gases have the same average kinetic energy. So the lighter gases are moving faster and the heavier gases are moving slower. So we could say something like this. Here's a heavy gas. Here's a lighter gas. Oh, and this is speed or velocity. Okay, I think something's crawling on my foot. I got to check it because I got scorpions out here. Nope, no scorpions yet. I get kind of freaky deaky about it because I hate getting stung by scorpions. It just hurts like hell. Anybody been stung by a scorpion? Really sucks. Okay, so we're going to just put all these gases. We got 1, 2, 3, 4, 5. So that's 3, 4, and 5. All right. So this is the average speed for each of those gases. And we're just going to position them. So our heaviest gas here looks to be HBr. So this would be HBr. What's next heaviest? Well, I got argon here. Here's argon at 40 grams per mole. Then I've got HCl at 36 grams per mole. Then I've got ammonia, NH3, at 17 grams per mole. And here is CH4. Now, this balloon has tiny microscopic holes in it. And think of it as a basketball basket. And if you're talking about how many baskets you make or how fast a gas will escape through that tiny microscopic hole, it depends on how many shots it takes. And how many shots it takes at the hole depends on its velocity, how fast it's moving. So the lighter gases, this is 16 grams per mole, 17 grams per mole. 36 grams per mole, 40 grams per mole, 80 grams per mole. Keeping in mind, they all have the same average kinetic energy. Methane here, as the lightest gas, is going to be taking more shots at the basket, and it will have the highest rate of effusion. Effusion is just escape through a tiny hole. Highest rate of effusion. Okay, so my answer for this one should be D. Is it? Better be.
Yes.
Do you understand? So if you see something that looks like this and ask you which one's the heaviest gas, well, the heaviest gas has the slowest speed. The lightest gas has the particles stretched out toward the higher speed. Okay, that's not terrible. How about one more, and then I'm going to call it quits, guys. I'm losing my voice, and I got to get up kind of early tomorrow, and I got a lot of stuff to do. It's been a long day.
Can
We
you
do
do
55.
question 49? Oh,
49?
No, it's okay. Yeah, we can do 49.
Have we done 49? No, this is a good one. Okay, we haven't done any quantum mechanics. I'll tell you what, let's do 49 and 50. Okay, and then we'll call it quits. Okay, which one of the following is not a valid set of quantum numbers? All right, let's look at the rules for quantum numbers. N is called the principal quantum number. And the principal quantum number tells you the distance from the nucleus. You can also say overall energy. And this is the big kahuna. So if this is the nucleus with some number of protons, the distance from the nucleus, those are the N values. Okay, so we would call this N equals 1, N equals 2, N equals 3, etc. It can have values of positive integers, 1, 2, 3, 4, etc. There really is no limit except for the elements of which we are aware in the universe. N equals 7 is all we need. Then we have the azimuthal quantum number. This, there's a couple of names for it. Azimuthal is the one I usually use, but regardless of the name, it gives us the shape of the orbital, okay? And the rules for the numbers are 0, 1, 2, 3, up to a maximum of n minus 1. So if n is 3, the maximum L number you can have is 2. If n is 2, the maximum L number you can have is 1. If n is 1, the maximum L number you can have is 0. Now we have another designation for the L values. L equals 0 is an S. L equals 1 is a P. L equals 2 is a D. L equals 3 is an F. I could go up to 4, which is a G, but I just really don't use that very often, but it exists. And this is where you find a lot of artificial elements or synthetic elements that we make. We don't really need it for the things that we normally see in reality. We actually have a lot of artificial elements that have an L value of 3 that are in an F subshell. Okay. Then we have the M sub L values. And the M sub L values are minus L through 0 to positive L. So if you have, let's say, an L value of 1, then your M sub L values will be -1, 0, and +1. If you have an L value of 2, which is a D subshell, that's going to be -2, -1, 0, 1, and 2. These are the orbitals, guys. These are the spaces where you actually put the electrons. So this entire set of 3 orbitals is a p subshell. Okay. This entire set of orbitals, L equals 2, is a D subshell. And then if you had L equals 3, that's an F subshell. You can put a total of 6 electrons in a P subshell, 10 electrons in a D subshell, and 14 electrons in an F subshell, because you've got -3, -2, -1, 0, 1, 2, and 3, 2 electrons per. Let's go over some rules first. Okay. If I'm going to fill up a P subshell, I have to start with a spin up electron here, a spin up electron here, and a spin up electron here. What do we call the rule that says for degenerate orbitals, you get the lowest energy level by having spin up for all of the degenerate orbitals? We call that Hund's rule. Are you with me, or have I lost you guys? I'm just going to
You're
say,
good.
okay, what do we call the principle when we pair up electrons, one spin up, one spin down? What do we call that?
Pauli exclusion.
That's it. That's Pauli exclusion principle. Okay. So you might see something like that. All right. Okay, now that we know the rules and we've gone over all this shit, let's take a look. This is the way we organize the orbitals. You start with the N value, then the L value, then the M sub L value, and then the M sub S value. All right. If I have N equals 3, is L equals 1 okay? Yes. If L is equal to 1, can I have M sub L equal to -1?
Yes.
Yes.
Yeah.
And M sub S can be -0.5. It would have been just fine if it were +0.5. How about this one? If I have N equals 1, can I have L equals 1?
No.
No,
No.
that is not legal because of the proscription that for the L value, it tops out at N-1. So this would need to be 0 for that to be okay. So B is your answer for 49. Everything else is okay. If N is equal to 2, L can be 0, M sub L can be 0, and M sub S could be -0.5 or +0.5. If N is 1, L can be 0, M sub L can be 0. We could have -0.5 or +0.5. Same thing for all those. These are all good. That's the only one that doesn't work. Let's do the electron configuration for gallium and call it quits. So this is a full electron configuration. So let's see, do I have a periodic table anywhere? I don't, so I'm just going to have to rely on my knowledge of the periodic table. So here we go. 1s2, 2s2, once we get to 2, we can have a P. So that's going to be 2p6. Then we go to 3s2 and then 3p6. And then we go to what? 4s2. And then we start the 3Ds. 3D, and we can put 10 in there. And then what do we go to? 4p, I'm sorry, yeah, 4p1. Okay, is that gallium?
Yep.
Yes.
Okay, so it looks like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So it looks like 50 is B. Okay, guys, let's do one other thing with it. Let's do core notation. So where would we stop for core notation? How about right here? So what is this the electron configuration for? That is
Argon.
argon. So core notation would be 4s2, 3d10, 4p1. Okay. Oh, 51 is an exception, right?
Yep.
Yeah, it's an exception. And let me go ahead and erase all that crap. Okay, the ground state electron configuration of the element 5s1 4d5 is what? Believe it's that, molybdenum. Okay, and the reason that it's an exception, if you look at molybdenum, you've got the 5s and then the 4d is sitting down here. There's 5 orbitals. And so you would think it would be 5s2, 4d4. Why is this not the electron configuration for molybdenum? Because this is not the lowest energy electron configuration. It's a better deal to take one of these 5s electrons, plop it down here in the 4d subshell. Now I have what? A half-filled shell. And then I'm half-filled here. But that's a higher energy orbital. So this is more stable. It's all about stability. All right, I will be in my office on Zoom at 2 o'clock tomorrow if anybody wants to join me then. And now I'm just going to wish you all a good night.
Thank you.
You bet.
Thank you. Good night.
Good
Good
night.
night, thank
Good
you.
night.
Take care. Get some rest, sleep.